In this video, we will talk about domain and range. Domain is a set of values of x in the relation. In other words, it's all possible x values in a function. Range is a set of values of y in the relation. Similarly, we can also refer to range as a set of all possible y values in a function. Let's talk about domain and range of these functions. So first one, we have a -1 and -3 on this point, and it goes on for forever. That's what this arrow means. It goes on for forever in that direction. So domain, all the possible x values are starting at -1, and then it goes on for forever to the x infinity. So we can say x has to be greater than or equal to -1 for domain. And for the range, we can say -3 and up. So y is greater than or equal to -3. For the second one, we have a quadratic function where we know it extends for forever in both directions of negative and positive infinity for the x. So domain will be all real numbers, and for the range, it starts at +1, and then the values of y are all smaller than 1. So we can say y has to be less than or equal to 1. Alright, for number 3, we have a rational function. So we have an asymptote at x equals to 2. So that means it's never going to cross the 2, but on both sides it's going to be reaching for those 2. So in that case, domain is x is all real numbers, right? Because it's increasing forever and it's decreasing forever. But x is not defined at 2, so x cannot be 2, but all real numbers. So if you write your answer this way, that means x is all real numbers except for 2. For the range, we have all the y values that's increasing for forever and it's decreasing for forever, except when y is equal to 1, it's not defined because that's an asymptote again. So we say y is not equal to 1. State the domain and range of each of these functions. So pause this video and try it on your own. Right. For the graph on the left side, we have for the domain, those are all of my possible x values. So x values are going for forever to the -infinity, and then it stops, right? That's what this closed dot means. It stops at 8. So domain will be, and sometimes we write it in a slightly different notation, x such that x is less than or equal to 8. Right. Miss Lee, why are we not just saying x is less than or equal to 8, but instead say x such that, that's what this stick means, such that x is less than or equal to 8. Well, in a higher level of math, we like to define our variable that we're going to be working with. It's completely possible to say x is less than or equal to 8, but we wanted to find the value x. X such that x is less than or equal to 8. Alright, what about for the range? Range is all of my possible y values, and it looks like y value goes on for forever on the positive side. But what about over here? We have -2, and then it goes up. So it will be y such that y is greater than or equal to -2. Right. For the graph on the right side, we have a quadratic that's concaved up. For the domain, those all my possible x and x values, it's going infinity in both directions, right? So then I can say it's all real numbers. And for range, y values are increasing forever, but for the minimum value right here, it's at -1. So we want to say y such that y is greater than or equal to -1. Not bad, right? In this slide, I have drawn 4 functions that are basics of everything that we will look at in this chapter, and I highly suggest that you know what these functions look like. For the first one, y is equal to x squared. That one's easy. It's just a concave up where it passes through the origin. So in this case, the domain is all real numbers. For the range, the ranges are all possible y values, so the minimum is at 0 and then it increases for forever, so we can say y is greater than or equal to 0. For the second function, y is equal to square root of x. Well, obviously when x is equal to a negative number, such as square root of -3, this cannot be a real number. This is a complex number, so it's not defined when x has a negative values. So it's starting at 0 because square root of 0 is 0. So starts it at 0 and then it goes in this direction for forever. So we can say that domain is x is greater than or equal to 0. For the range, those are all my possible y values. We can say y is greater than or equal to 0. For the third function, which is a rational function, which we sometimes say it's a fractional function, when x is equal to 0, right? When denominator is equal to 0, it's undefined. So actually over here, we have an asymptote. And for the y value where it's not defined, we'll talk about this later, but as x goes to infinity in both positive and negative, it's not defined on zeros. So y equals to 0 is another asymptote. So we have for the domain, x cannot be 0, and for the range, y cannot be 0. Something interesting about these rational functions is that they always come in pairs. If you know that one of the graph exists in the first quadrant, then you know the other pair exists in the third quadrant. Same idea. If you know one of the graph exists in the second quadrant, the other pair appears on the fourth quadrant. Number 4, which is y is equal to 1 over square root of x. If we look at this, where the denominator goes to 0, well, when square root of x is square root of 0 is a 0, but we know 1 over 0 is undefined. So x cannot be 0. So when x is equal to 0, that is my asymptote. Similarly, when x goes to positive infinity, it gets really, really close to the x-axis, but it's never going to cross that x-axis. So when y value is equal to 0, that's another asymptote. So for this function, y is equal to 1 over square root of x. It's kind of like number 2 and number 3 combined, right? Y is equal to square root of x, and y is equal to 1 over x. When you combine them together, you kind of get a function that looks like 1 over square root of x. So using that information, we can find the domain and range. Domain has to be x is greater than 0, right? X is not defined when it's negative numbers, and x is also not defined when x is equal to 0. So x has to be greater than 0. For the y, it also needs to be greater than 0, because you're never going to get an output that's negative number, because even if you plug in a negative number for the x, that does not, so for example, when x is equal to -3, we have 1 over square root of -3. That's not equal to -1 over square root of 3, right? Those are not the same thing. So for the output value, you're never going to get a negative number. So it's not going to cross the x axis. Find the domain and range of these functions. First one is f of x is equal to square root of x minus 5. We know that we cannot have a negative number inside the square root, but we could have a 0 because square root of 0 is a 0. So x minus 5 must be greater than or equal to 0. So that leaves us to believe that x has to be greater than or equal to 5. Let's try to graph this. So when we have x is equal to 5, that's square root of 0, so that's going to be 0. And then the rest is just plug in some numbers that are going to work out nicely. So for example, if x is equal to 9, we have square root of 9 minus 5, that's square root of 4. And we know square root of 4 is equal to 2. So 1, 2. Over here, when it's 9, it's going to be 2. Similarly, if x is equal to 14, we have 14 minus 5, that's square root of 9. So square root of 9 is 3. So you know generally this function is going to be increasing as x is increasing. So we can say the domain of this function is x such that x has to be greater than or equal to 5. The range of this function, all of my y values, will be greater than or equal to 0. So y such that y is going to be greater than or equal to 0. Alright, let's look at the second function. F of x is equal to 1 over x minus 5. We know when the denominator is equal to 0, it's undefined. So when x is equal to 5, the function is undefined. So we know if we were to graph this, at x equal to 5, that's where the asymptote is. And let's plug in some numbers to see what the graph is going to look like. If x is 6, it's 1 over 1, so that's going to be 1. So when x is 6, it crosses at 1. Same idea, as x gets bigger and bigger and bigger, we're dividing it by 1 divided by bigger and bigger and bigger numbers. What happens when you do that? For example, 1 divided by 10, 1 divided by 20, 1 divided by 100,000, you know the number gets smaller and smaller and smaller. So from 6, it gets smaller and smaller, so it gets close to the 0, but it's not going to pass the x-axis. What about when x is equal to 5.5? So that's in between the asymptote and number 6. So in that case, we have 1 over 5.5 minus 5. So that gives us 1 over 0.5. But 1 over 0.5 is equal to 2. So when it's 5.5, different color. When it's 5.5, we're at 2. So after, just plugging some numbers and playing it around, you know this number is going to increase. And since it's an asymptote, it has an asymptote at 5, it's not going to cross the 5, but it's going to get really, really close to 5. And since this is a rational function, like I mentioned from the previous slides, it comes in pairs. If you know one of the graph is appearing on sort of like the first quadrant, then you know the other one is happening on the third quadrant. In this case, we can also find the y-intercept by plug in x equal to 0. So in this case, it'll be 1 over negative 5, which is negative 0.2. You could leave it in fractions or you could leave it in decimals. So this is what the graph looks like. So then now domain would be all of my possible x values. It's going negative infinity all the way really close to 5, and then 5 all the way to positive infinity. So x is defined everywhere except when x is equal to 5. So x such that x is not equal to 5 will be my domain. In other words, x is all real numbers except for 5. How about range? Range is all real numbers for y, but y cannot be 0. Right? Because it gets really, really close to the 0, but it does not cross that x-axis. Same idea as it goes to infinity. As x goes to infinity, it doesn't cross the x-axis, but it's getting really close to the y value of 0. Alright, lastly, we have f of x is equal to 1 over square root of x minus 5. We know the denominator cannot be 0. If so, then it's undefined. So x minus 5 must be greater but not equal to 0. Right? So that means x is greater than 5. So let's try to graph this and see what it looks like. So when x is equal to 5, that's where it's undefined. So that's where my asymptote is going to be. X equals to 5. Can I have a value that are less than 5? For example, if x is equal to 4, you're going to get square root of negative 1, which is a complex number, so it's not a real value. So everything that's left side of x equal to 5, the value does not exist. But how about when x is 6? When x is equal to 6, we know the value of y is at 1. So when it's 6, so similarly, as x is increasing, you're dividing it by a bigger and bigger number. So it's going to get closer to the 0. And then it's not going to cross that x-axis. If you plug in the numbers that are in between x equal to 5 and 6, you'll notice that the value is increasing. So it's going to be similar to the one that we have on the left side, but that's what the results will look like. So domain would be x has to be greater than 5, and range will be all greater than 0 because it's not going to cross the x-axis.